started with a simple design and worked our way up to a design that, during the test, actually turned out rather well. Now, in an overview of the presentation, we'll be discussing the bridge structure, which Philip will talk about, the bridge development, which Seth will cover, and I myself will cover the conclusion, which will discuss what we learned and how we can apply it to everyday life. So I'm going to go ahead and turn it over to Philip, who will take it from here.
When we were building our bridge, we had four main design emphases. The prevention of deflection to allow our bridge to withstand testing for longer. The use of equilateral triangles because they're one of the strongest geometric shapes available. Using as few popsicle sticks as possible because they're too heavy. And compressibility of balsa wood because it'll get stronger as it's compressed more. And the first principle of preventing deflection, we want to make sure it didn't deflect too much or else the tester would stop working before they got the full effect. And the computer program we used, Model Smart 3D, would actually calculate the deflection for us automatically. So we were able to modify our bridge to help combat that. And we did that by leaning out the towers like that, so the cables would pull out against the bridge, helping to pull the bed back up, and notching the members in the bed so they would pinch each other together when it got pushed down. And the second principle we used was equilateral triangles because they'll cancel out the force. Because when the force of gravity is applied on it, the normal force and internal tensional force will cancel out individual force vectors. And even if we weren't able to make all the triangles perfectly equilateral, then it would still be able to cancel out some measure of the force applied to them. The third principle used was limiting our usage of popsicle sticks as much as possible because we found that they were too heavy to create an effective weight ratio, especially when we could get almost the same strength out of just using balsa wood. So we ended up having to use the popsicle sticks in one location on our bridge, and that was the base of the tower. Right in there, where the towers and the bed supports connected. Because we had all the joints coming together into one spot, and we didn't have enough room just to connect them all onto one little piece of wood. And the last principle we wanted to think about was compressibility. Because we figured that the more we can compress a piece of wood, the stronger it'll be. And we tested this in Model Smart by using a little rig like this, where we would have the force going down on a straight member of balsa wood. And when we tested that, we got these results, where, as you can see, after about 2 inches, then the maximum load of it severely drops off. Like, up before that, they were all relatively similar. So when we were actually building our bridge, we tried to keep as many members that would come under any sort of compression below 2 inches. So we tried to integrate these in all of our components, which Seth will tell you about.
So our bridge components included the bed truss system right here, the bed support trusses, which are the supports for the bed, and then just 3-sided towers and bases. So to start off with the bed, we try to make it light and strong, like our whole bridge is. And to do this, we use a ton of equilateral triangles to cancel out as much of the force applied to it as possible. We found that the double worn with verticals has a lot of equilateral triangles, but in the center of our bridge, we had 2 just single worn with verticals, just because we found in the program that there wasn't much force being applied to them, so we just got rid of the extra weight there. And then also, as our max weight increased, we added some K-trusses into the bed so that to support the double worms as the weight increased. So also we had to have something. My bad. But anyways, we had to have something internally within our bed. So what we did is we put in a V as you look down the bed. I'll have a picture in a second for you. But we had a V in the center of the see here, this is the inverted V, well, not inverted, but the V right here is originally going to be just a triangle, but we kept it in a 5/8 inch slot for the testing rod. So, and now we needed to support our bed. So we had two ideas. We had the arc, because we knew that was a strong structure, and just straight members going up to the bottom of the bed. But unfortunately, when we tried the arc, it wouldn't work because arcs work with, you need proper abutments for arcs to push the force back up to the center, the center member or stone of the arc. But unfortunately, due to the dimensions, we could not make a proper arc. So we decided to use straight members, but we made a truss system within the straight members to make them stronger. So, as you can see here, when we tested the models in our 3D, the max load for the arc was a lot less than for the straight members with the truss system integrated in them. And these are the pictures. So right here we had straight members going up. I don't know if you can see, but we made another truss system within them if you were to look underneath the bed. And then the arc, we didn't have proper abutments right here and here to push the force back up into here to make the center strong. So next we have our two towers. And originally we wanted to make them with a large base, because those are normally stronger, but due to, again, the dimensions of the bridge we had to follow, we did not have enough room, so we had to find something else to do. And so we decided to have them leaning out and have them only three-sided to cut down on weight, and three sides we made an equilateral triangle to cancel out any horizontal force on it. So here are the towers, and what we found that is really cool with the towers is, as earlier, this joint right here is really important. And so as the force comes down into here, we didn't want this to slide out on the testers at all. So with the towers leaning outwards, what we did is we had it at an angle so that this inner member right here of the towers, it was in line straight down to this joint. I don't know if you can see that. So that hopefully when the strings pull, it would keep this one joint in place. So those are our towers, and these are the results we got in the Model Smart 3D. Big base, just because of the dimensions, we couldn't quite get that to work, and the pyramids laying out worked a lot better. So, and here's the pictures. This is what we're going to do. And as you can see, the force goes down right into here, into this member, where this joint would be. And what I was talking about earlier, the horizontal force right here, these are equilateral right here. So we were hoping that it would cancel out as much of a horizontal force, since there's both horizontal and a vertical force. And now I'll turn over the conclusion to Stuart.
Now, of course, with all designs, there were a few obstacles we encountered during the design process, one of which was connecting the base to the tower, which we developed using CAD software. Unfortunately, we didn't know the results. We predicted them to be around 200 to 250, and we ended up with a total of 168. So it was a little shorter than expectation, but that was fine with percent of error. Next was integrating the cable stay portion without the CAD software. That was interesting. We had to use a lot of outside mathematical formulas. Again, it was a lot of guesstimating, but in the end, we were right around where we wanted to be. Maintaining the weight load, we had to focus a lot on limiting popsicle sticks, and at the same time using balsa wood with our equilateral triangles to keep it in equal force, so that we're still, for every gram you're using, you're making up for 3 or 4 grams of weight load. Now, this was basically the final product here. And the idea started with basic theories on models. We picked a couple. We started, as you can see from this one, and we came all the way to this one. Started with a lot of basic models and combined them to make a near hybrid model, I would call it. Now, the construction, we did a big step-by-step process. One of our key elements was using the miter box, which enabled us to use a lot more accurate cuts in building the model, as well as have shorter drawing times for glue, because the pieces were so well say he's now more of a mathematician and surgeon in my eyes for his accurate cuts. Sets an architect